chapter 19, and now we're going to take a look at, we talked yesterday about how those charges move. Today we're going to look at the fact that these charges actually don't move quite as easily as we think they do. It turns out that they will often run into stuff which causes them to slow down. We actually have a name for that. So we're going to start off with talking about drift velocity. Now, initially, everybody thinks, oh, well, here's your conductor right here, and these charges are in like this. And all of a sudden, zip, they go right along. And they kind of think of kind of like a super highway. And so those charges just go flying around, no problems, no worries. But it turns out, in reality, that when you have your conductor, there's actually stuff in the way. And so these charges have to go through. And so if this is my charge, here's my electron. As it comes through, it's trying to go through, and all of a sudden it hits O, it comes through, oh, hits O, hits O, oh, goes through, hey, I got a nice path here, and zip on through, and I just got lucky because of how I drew it. But these charges suffer collisions with particles inside the conductor. So conductors aren't quite as nice and happy as you think of. I kind of think of maybe as like a road with a lot of potholes, okay? You go and also, boom, you hit one, you slow down, whether you want to or not. So, but it turns out that the more collisions there are, the slower the charges go. And what's neat about this, and you kind of think about it, a better analogy here, if any of you have ever seen The Price is Right, in Plinko, that game where you put the thing up on top, these charges are getting pushed. Now, I know I slipped back into the electron thing. I should probably be doing positives. I apologize, but you get the idea. Remember, we had that conversation. So remember, this is your high energy over here. Here's your low energy here. So it's like it's going down a hill, and it's just running into stuff. And so every time it hits, it's going to slow down. It's going to give up a little bit of that kinetic energy that it had, and it's going to go into something else. And so what we can say is that the more collisions there is, the more work done, the slower the object goes. And so what's happening is during the collision is taking some of that energy. Kinetic energy of that charge, because the charge has a mass, it has a velocity. When it goes through, it hits, it slows down, it has to lose that kinetic energy. That kinetic energy is turning into some other type. And we will talk about that a little bit later on. These collisions can be named under the subheading of resistance. Resistance is the opposition that a conductor will give to the current going through it. Okay, and so remember, the more collisions, the more resistance there is. And so if we look back at my initial one, here, I had a lot of resistance. And again, maybe you can look at this in two different pieces, but I had a lot of resistance here. I had a lot of collisions. But then it got into this part, and I'll just circle this in blue, got into this part, and it didn't have as many. And so I would have more resistance in the highlighted section than I would in the other section. And now generally that's not the case. Generally, if you have a material, that material is relatively uniformly resistance all the way through, okay? But our units for resistance, actually, I'll give you the symbol first. The symbol of resistance is a capital R. Yay, something that makes sense. The units, however, are measured in ohms, O-H-M-S, okay? And rather than write that in O, we can't because O looks an awful like a zero. You don't want that. We use the Greek letter omega, a capital omega. So it kind of looks like a horseshoe. This is my version of it. There's probably better looking ones out there, okay? But it's kind of like a horseshoe looking thing, okay? This is the symbol for ohms, okay? And so we're going to measure basically the number of collisions and how much it resists that charge going through it in ohms. We'll talk about that here in a second. Ohm's law, and this came from a guy by the name of George Simon Ohm, and that comes, I believe, on the next page. Where is it? Yep, there it is, coming down. Okay, this is named after a guy by the name of George Simon Ohm. But basically, what Ohm did was he showed that the greater the amount of voltage you had, the greater the current. Okay, and so I'm going to go back to that analogy of the river. And you can kind of think of the I, the current, as how fast the river is flowing. Okay? The voltage, that is the change in energy. And so if you have a large change in energy, let's say like it's a mountain stream and there's a huge change in elevation, the current goes fast. If it's a low change in elevation, like Bust-Eye Creek, there's a change of maybe a couple feet over a mile or so, that water goes really, really slowly. And so we're relating how fast the charges go to how much that changed in energy. And this should make sense. It is a direct proportion, a direct proportionality. Well, if you were to graph this and show that direct relationship, and I'll put this in black first, and we'll do, I'm going to do this kind of reversed. I realize I'm switching my dependent and my independent variable, but there's a rationale and a reason for that. Regardless, I have a direct relationship. Okay? This shows me that as my voltage goes up, my current goes up. Or actually, I know I switched them. Okay? But it is a direct relationship. Well, if you had something that had more resistance, it would have a smaller amount of current change when you increase the voltage. And so I'm going to put another graph here. This would be, oh, my voltage went up, but my current didn't go up as much. Yeah, okay, or vice versa. And so basically here, again, we still have that direct relationship, but now the slope has changed. Well, the slope of this graph is equal to, change y over change in x, so the voltage over the current. This slope actually is equivalent or equal to the resistance of the material. The different slopes tell us, oh, I've got a good, if I have a higher resistance, then it's going to have a less of a current change when my voltage changes. If I have a smaller resistance, then I'm going to get a bigger current change through a smaller voltage change. But this is our direct, this is actually going to be Ohm's consequence. I call it Ohm's consequence. It's kind of a variation of Ohm's law. Okay, Ohm's law technically is this, that the voltage is proportional to the current, or current is proportional to the voltage. I call this Ohm's consequence because it links back and it shows that direct relationship. And it talks about how that slope is actually going to be equal to the resistance of the material. Now, George Simon Ohm was the first one to state this relationship. And basically that the current flowing through a metal conductor, it doesn't have to necessarily be a metal conductor, although generally that is. But there is one thing I want to point out, and I have to highlight this, at a constant temperature. Because it turns out that if you have different temperatures, your resistance will change. And we're actually going to show that in a lab we're going to do. But you will see this in your reference table generally as R equals V over I. But it's very easy to rewrite that into V is equal to I times R. Or the one that I more like, so let me change colors. I don't want to be in the same green again. Or the one that I kind of like a little bit better, the current is directly proportional to the voltage, but it's inversely proportional to the resistance. So as voltage goes up, current goes up, but as resistance goes up, current goes down. So that's what I mean by the formulas there. Okay? Now, as we stated, different materials have different resistances. And it turns out that modifications to the physical quantity, physical attributes of that material will also change its resistance. Okay? And so we're going to do a lab on this. And I'm going to show you this oh, wow, that was kind of ugly. Hang on one second. I'm going to show you this animation and let you play around with it so you can kind of see it a little bit better. But basically, here's what you need to know. Is that generally, as the length of the conductor goes up, the resistance goes up. And I'll give you an example tomorrow in class, and I'm probably God willing, we'll be able to mingle, and I'll be able to show this because this works really well with a live person and live people demonstrating this. But the longer you go, the better chance you're going to have a collision. The more collisions you have, the higher resistance you have. It's also inversely proportional to the area. The wider the area, the less chance you're going to have a collision. And the example I like to give here is if you compare the hallway outside my room, it's only 3 blocks wide. Where if you go to the main hallway, it's actually 8 blocks wide. And so if you're walking down my hallway, there's a better chance you might have a collision with somebody coming the other way than if you were going down the main hallway, because you could easily avoid them, or much more highly likely you could avoid them. Okay? And the second to last thing we're going to talk about is that the resistance is proportional to something called the resistivity. This is the Greek letter rho. And it turns out that different metals will conduct electricity better or worse. This is a constant. Actually, that's the symbol rho, but it stands for the resistivity. Resistivity. And it's a constant for a material. And you don't have to memorize this. This is actually in your reference tables in the lower right-hand corner of the electricity section. You can see it talks about resistivities at 20 degrees. Okay, and it gives you I'm trying to go on. Copper's 1.72 times 10 to the negative 8. Silver's 1.59 times 10 to the negative 8. Aluminum's 2.82 times 10 to the negative 8. Nichrome's 150 times 10 to the negative 8. And we will talk about that one a little bit more. But different materials have different resistance, just the amount of stuff that's in there that you can have collisions with. Now, the last thing we're going to talk about in this is temperature. And these ones, by the way, if I put all these together, before I go into temperature, I'm going to give you the equation that's in your reference table, because that throws it all together, which states that the resistance of a material is equal to the resistivity times the length divided by the area. And this will let you find the resistance of it at a constant temperature, because this resistivity changes with temperature. And generally what we can say is that as temperature goes up, the resistivity goes up. As temperature goes down, the resistivity goes down. And I'll put that right here. As temp increases, resistance increases. And this is generally, not always, but as temperature decreases, the resistance will decrease. Okay. And again, we'll talk about that a little more. We'll do some examples. Now, the last thing I want to talk about in this segment is superconductivity. Superconductors are rare materials that exist, and when they have their superconductive properties, their resistance essentially falls to 0. Now, the advantages of this is, remember, every time a charge has a collision, it's going to lose some of its energy, and it slows it down. Well, if you don't have any collisions, you don't lose any energy along the way. And so all of the energy you would have at the beginning would be usable energy you would have at the end. Okay? Generally, we lose when the more you push, the longer you have to transmit electricity, the more loss you're going to have, and the more energy you're paying for, which you aren't actually getting a chance to use. So we'll talk about this a little bit more. We'll talk about how its temperature is really low. We'll give another couple examples, and I'll explain it a little bit better tomorrow. But everybody have a great night. We'll see you tomorrow. Bye.